In this video, we're computing the period of oscillation for a meter stick drilled on the 10 centimeter mark, oscillating on a hinge. So we're given the mass of this thing as 200 grams, and we're asked to use the parallel axis theorem to compute the moment of inertia of the stick, and then we want to compute the period of oscillation. So here's a reminder of the parallel axis theorem, and I'll post a link up at the top to where this was first derived. The idea is that if you can compute the moment of inertia of an object about its center of mass, and then you want to rotate it about some other point, you just take that moment of inertia about the center of mass, and then you add in another term, md squared, where d is the distance between those two parallel axes. So in the picture of our rigid body, the center of mass axis that's pointing out of the page and passing through the center of mass of the stick, and then our actual rotation axis is going to be at this 10 centimeter mark where we drilled a hole through the stick. So the d is 40 centimeters for us. So we also have to remember, what's the moment of inertia of a uniform rod through its center of mass? And this was also derived in a previous video. That turned out to be 1/12 ml squared, where m is the mass of the stick and L is the total length. So now we can get to applying the parallel axis theorem to find the moment of inertia with respect to our actual hinge. So we get a 1/12 ml squared. That's the moment of inertia with respect to the center of mass. And then we tack on this second term from the parallel axis theorem, m times d squared. So this really is a numerical problem, but we can make some progress symbolically. I can factor an m out, and that leaves me with a 1/12 ml squared for the first term. And then our d is 40 centimeters, which is actually 0.4 times the total length of the stick, because the stick had a length of 1 meter. And 0.4 is 2/5. So d is 2/5 L, and we're going to square that. So now we can pull out an L squared, and we have to add a couple of fractions that aren't really cooperating very well. One is 1/12 and the other is 4/25. And with no common factors in those two numbers, we end up with a huge common denominator of 300. Since I'm already going down this road of writing down a symbolic solution, let's just get the denominator of 300 on this. So I multiply the first fraction by 25/25, giving me 25/300. The second fraction, multiply by 12/12. And that gives me 48/300. So add those two up, 25 and 48, gives me 73/300 times ml squared. All right, what I really wanted here was just a decimal approximation. So let's plug those numbers in. And my mass was 0.2, and my length was 1 meter. And that was a 300 down there. And to three significant digits, we get an approximate moment of inertia of 0.0487. And the units of moment of inertia, recall, are kilogram meters squared. All right, so now we get into the calculation of the period of oscillation of this thing. And we just derived this in the previous video, and I'll post a link to that up at the top. The period of oscillation of a physical pendulum turned out to be 2 pi times the square root of its moment of inertia, I, over mg r center of mass. So r with a subscript of cm. In that derivation, that was the distance between the hinge, the actual rotation axis, and the center of mass of the rigid body. So that's the same as d for us. In other words, it's 0.4 L or 40 centimeters. So subbing into the formula, I get 0.0487. Now that actually came from a repeating decimal, 0.04866, and so on. So when I run this in my calculator, I'll keep the extra precision. And then our mass was 0.2. G, we'll use the approximation 9.8. And then R, center of mass, the distance between the rotation axis and the center of mass is again 40 centimeters or 0.4 meters. And when we run the numbers on this to three significant digits, we get about 1.57 seconds. So if you're a physics teacher or a particularly motivated student, this is one of the easiest demos that you can do in the classroom. You just drill a hole through the 10 centimeter mark of a cheap meter stick, stick it on a pencil, and watch it oscillate and see how close you get. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.